Review of Thevenin's theorem and Norton's theorem before we start understanding about maximum power transfer theorem. What is exactly what exactly is maximum power transfer theorem? What exactly we have learned in Thevenin's theorem and Norton's theorem? So for that purpose, let me first give you the review of Thevenin's theorem. In case of Thevenin's theorem, a complicated network was replaced by a single voltage source in series with a single impedance. So in case of AC circuit, we were talking that it is a single impedance. In case of a DC circuit, it was represented as a single series resistance. So actually, we have dealt with two different kinds of circuits there. One is DC circuit, the other one is AC circuit. In both the cases, for DC circuit as well as the AC circuit, we have considered both independent voltage sources, independent current sources, dependent voltage sources and dependent current sources. So considering the dependent sources as well as the independent sources, we have done Thevenin's theorem. That means we have analyzed the circuits, various circuits, by applying Thevenin's theorem. That means the current through a particular element or voltage across any element, or it is the power dissipation in any element after having found out the current or voltage. So that we have done it there. Next, in case of Norton's theorem, the same circuits, AC and DC circuits, we have replaced it by its equivalent current source. Actually, the practical current source is nothing but an ideal current source in parallel with a resistance or impedance. So, in case of Norton's theorem, or in case of the application of Norton's theorem, we have actually transferred, or we have actually simplified a complicated network into into a practical current source in parallel with an impedance. So, with all this brief introduction about Thevenin's theorem and the Norton's theorem, let us now concentrate on maximum power transfer theorem. So, what exactly we mean by maximum power transfer theorem? As the name itself specifies, the maximum power transfer is the power that is being transferred from the power that is to be transferred from a source to the load. We actually have to calculate the power that is being transferred from the source to the load, and that power which is being transferred from source to the load must be maximum. That is, when we measure the power across the load, it should be maximum. So now actually, according to the maximum power transfer theorem, a maximum power will be transferred from the source to the load. How it is going to be done? So for that, let us first understand the statement of the theorem, and then we analyze or understand exactly how we can apply maximum power transfer theorem to find out the power which is maximum in various cases. So now, what is a statement? Statement of the theorem, that is maximum power transfer theorem, is different for DC circuit as well as AC circuit. So what is a statement for DC circuit, and what exactly we are going to understand in case of AC circuit? So first statement, it states that in a linear active bilateral DC network, that's what is being mentioned here, because DC circuit and the AC circuit will have different values for the maximum power transfer theorem. So it is a different statement, we are going to do it here. So it states that in case of DC circuit, a linear active bilateral DC network, the maximum power will be transferred from source to the load when the external load resistance equals to the internal resistance of the source. So when you have a simple series circuit wherein you have a source in series with a resistance, to that if you connect a variable load resistance, and if you start varying the resistance there, the maximum power is going to be achieved when this variable load resistance value becomes equal to the internal resistance of the source. That's the meaning of the first statement. Next we have, it states that in an active AC network consisting of source with internal impedance Zs, which is connected to a load ZL, the maximum power transfer occurs from source to load when the load impedance is equal to the complex conjugate of source impedance. Even in this case, we have a source, in series with a source we have an impedance, and at the load side also we have a variable impedance there. So variable impedance means an impedance, if you say, it will be consisting of both the real part as well as the reactive part. So then when we apply or when we go for the maximum power transfer in case of AC, then in that case both the real part, which is resistance, the reactive part, which may be inductive reactance or capacitive reactance, should be varied. Both of them should be varied. Both of them are variable in that case. When we vary both of them, the impedance value at the load will be so adjusted that the magnitude of that, or the value, is equal to the complex conjugate of the source impedance connected over there. That is the second statement. Next, coming to the last one. So assume that you have AC source in series with an impedance, but at the load side you have only a pure resistance. In that case, what will be the condition when the maximum power is going to be transferred to the load? In that case, if the load is pure resistance, then for maximum power transfer takes place when load resistance is equal to absolute magnitude of the source impedance. You know that the magnitude is nothing but equal to square root of r square plus x square in case of impedance. So when you find out the magnitude of the source impedance, the load resistance will be adjusted in such a way that the value of load resistance is equal to only the magnitude of the source impedance. So generally, for maximum power transfer theorem, we have to give all the three statements, one for DC circuit and two for AC circuit. One says if the load impedance is an impedance and source is also having an impedance, in that case the load impedance should be equal to the complex conjugate of the source impedance. But if you have only the resistance as a load, then in that case the load resistance must be equal to the magnitude of the source impedance. That's the meaning of the statement over here. Next, let us try to understand by analyzing the circuit for a simple single circuit. So now what is it? Proof we need to find out, we have to prove that whatever we have just now stated is correct. So for that we have to prove the maximum power transfer theorem here. What does it say? Now consider the electrical system with load as shown below. So you have an electrical network here and the load is connected, to which we are going to determine the value of load resistance so as to deliver the maximum power to the load. So this is a simple circuit or simple block diagram representation here that I am using. So you need to have an electrical network and a load connected there. This electrical network can be anything. It can be only a single voltage source in series with the impedance, or it may be a network. If you have a network, in that case you have to replace that electrical network by Thevenin's equivalent. It is not Norton's equivalent, it should be by Thevenin's equivalent. So because Thevenin's equivalent is nothing but a series, it's nothing but a voltage source in series with an impedance, and hence we have to replace that electrical network which is before AB by the Thevenin equivalent, and to that you connect the load. Load may be a resistance, impedance, or maybe another circuit also. Just see here, electrical system may be a complex circuit consisting of several elements and sources. In such cases we can find the maximum power transfer with the use of Thevenin's equivalent circuit. That means that complex network must be replaced by Thevenin's equivalent circuit. So that I am going to have at the left side, that is the left hand side of the circuit, I will be having only the voltage source in series with an impedance, and the right hand side I will be having of the circuit or the resistance. Replacing the complex electrical system with its Thevenin's equivalent circuit, we get the circuit shown below. The circuit, whatever we have it here, is V Thevenin, R Thevenin and RL. RL, it's a variable load resistance which I am going to have it. So generally for understanding maximum power transfer theorem, or in order to prove the maximum power transfer theorem, we generally use this simple circuit here. So now we have to prove that the maximum power is transferred to the load resistance when the value of this load resistance becomes equal to the Thevenin equivalent resistance, or it is the series resistance of the source. So from the previous circuit, from the circuit whatever we have it, a single series circuit wherein we have an voltage source in series with two resistances over there. One is the load resistance, the other one is the series resistance or the internal resistance of the source. So from that circuit, the current flowing through the load, if you go back to the previous circuit here, you can just see, you can find out the current that is flowing through the load here. What is it equal to? If you apply Ohm's law, you can easily say that these two resistors are connected in series, that is R Thevenin and RL are in series. So the total resistance of this loop is R Thevenin plus RL, and to this loop a voltage of V Thevenin is applied. So you can find out the current by applying Ohm's law, and it states that it gives the value of current that is flowing through the circuit as V Thevenin divided by sum of these two resistances. That's what is being given here in the case. I is equal to V Thevenin by RL plus R Thevenin. So this is the amount of current. And we all know that the expression for power dissipation is given by either V into I or I square R or V square by R. So now since we have found out the current I here, we can use a expression I square RL. So the power transferred to the load PL is equal to I square RL. And for I, substitute the value I equal to V Thevenin by RL plus R Thevenin. So it is V Thevenin by RL plus R Thevenin the square into RL. So here, since we have to transfer the power to the load resistance, where load resistance is a variable, for the maximum power transfer, we have to differentiate this expression, that is PL, with respect to RL because RL is variable, and equate it to 0. So here RL is variable. So the condition for maximum power delivered to the load is determined by differentiating PL, load power, with respect to the load resistance and equating it to 0. So it is the partial differentiation which we are going to carry out. So only one variable that we are having here is RL. So it is dou PL by dou RL, which is equal to, the expression is I square RL, where I square is equal to V Thevenin by RL plus R Thevenin the whole square. That's the expression into RL. That's what is the thing we have it. So if you differentiate it, it is the differentiation of division, that is U by V method. So using that, we can do it as V Thevenin square, which is a constant, just keep it out. Then RL plus R Thevenin, already it is whole square, that whole square. So generally when you do it, RL plus R Thevenin the whole to the power of 4, keeping the denominator constant, differentiate the numerator. Here RL, so when you go for the differentiation of the division, that is U by V method, then what exactly we are going to do? So this is going to be square, and then keeping this as it is, then differentiate the numerator, minus keeping the numerator as it is, differentiate the denominator. So that's what is being done here. RL plus R Thevenin to the power of 4, RL plus R Thevenin square minus, so differentiating the denominator. Denominator is RL plus R Thevenin the whole square, so that it is 2 into RL into R Thevenin plus RL. That's what you are going to. 2 into R Thevenin plus RL into 1 is for the denominator, and keeping the numerator as it is, that is RL as it is, this is the expression we are going to give it. We are going to get it. That should be equal to 0. So that V Thevenin square by RL plus R Thevenin to the power of 4, if you cross multiply that, that's going to become 0. Then what do we have? We have only the numerator part, which is nothing but equal to RL plus R Thevenin square minus 2RL into R Thevenin plus RL equal to 0. That will be the numerator part. That remains this constant part, that is V Thevenin square by RL plus R Thevenin to the power of 4. The entire thing is going to become 0 if you cross multiply. So simplifying it further, I get the next step, which is RL plus R Thevenin's whole square is equal to, that is transferring this negative part to the right hand side, I get 2RL into R Thevenin plus RL. So RL plus R Thevenin the whole square, simplifying it further, I get RL plus R Thevenin is equal to 2RL. RL is equal to R Thevenin. So it is only the simplification part which you need to do it. So only thing is, since RL is a variable, you have to differentiate the load power with respect to RL and equate it to 0 to get the condition for maximum power transfer to the load circuit. So now that is what is being stated earlier. So when the load resistance becomes equal to the series resistance of the source, or it is the Thevenin's equivalent resistance, then the maximum power will be transferred to the load resistance. So this is the proof of the theorem. That is for the first case. Then we have to prove the second and the third case also. So to prove the second case, so what is that we are going to have it? So before that, what will be the power transferred? Actually, we have found out the condition for the maximum power. The next thing is, what will be the power transferred during this condition? So then we have the expression PL, which is equal to I square into RL. So in place of RL, you just substitute R Thevenin. So if you substitute that, you get V Thevenin by R Thevenin plus R Thevenin, that is 2R Thevenin, you are going to have it, the whole square into R Thevenin. So this is the expression for power. So this is 4R Thevenin square in the denominator, and in the numerator you have V Thevenin square into R Thevenin. So R Thevenin in the numerator and R Thevenin in the denominator gets cancelled, so that the expression finally you are going to get for the maximum power transfer is, or the power which is the maximum power which is being dissipated in the load impedance is equal to, or load resistance is equal to PL, which is equal to V Thevenin square divided by 4 into R Thevenin. So after finding the condition for maximum power, substituting the same condition here, we have got this particular expression, that is for the load power which is being transferred, and also we say that it is the maximum. Next, proof of the maximum power transfer theorem for AC circuit. So as soon as we have an AC circuit, you can just observe here, we have the Thevenin's equivalent voltage itself, because complicated circuit was replaced by Thevenin's equivalent voltage, or sometimes it may be a single voltage source in series with the impedance. Both the cases appears. So now here you have an impedance Z Thevenin, which is equal to R Thevenin plus JX Thevenin. That's how we are going to represent an impedance, R plus JX. Similarly, the load impedance here, RL plus JXL. So the same thing I have written. Let ZL equal to RL plus JXL and Z Thevenin is equal to R Thevenin plus JX Thevenin. Then how to find out the current through the circuit? Once again, the current through the circuit I is equal to V Thevenin divided by sum of these two impedances. Since these two impedances are represented in their rectangular form itself, it's easy for you people to find out the equivalent impedance. What is equivalent impedance? Z Thevenin plus ZL, or the sum of the impedances here is equal to Z Thevenin plus ZL, where it is nothing but equal to R Thevenin plus JX Thevenin plus RL plus JXL. And you all know that to add the two complex numbers, you have to add real numbers separately and the imaginary numbers separately, so that it is R Thevenin plus RL plus J into X Thevenin plus XL is the sum of the impedances we have it. So once you find sum of the two impedances, you can find out the current I by applying Ohm's law, which is equal to V Thevenin divided by R Thevenin plus RL plus J into X Thevenin plus XL. That's what is given. I is equal to V Thevenin plus Z Thevenin plus ZL, where it is the same thing whatever I just now spoke. I is equal to V Thevenin by R Thevenin plus J X Thevenin plus RL plus JXL, or I is equal to, so separating the real and the imaginary parts here, you can just observe RL plus R Thevenin then plus J into XL plus X Thevenin. So now in this case you have two variables, one is RL, the other one is XL. R Thevenin and X Thevenin are the resistance and the reactive part of the Thevenin's equivalent circuit. RL and XL is of the load, and hence both are variable. RL is variable and XL is variable. So in such cases, how to find the condition for maximum power? The first thing is, you have to find out the expression for the power delivered to the load. What exactly we are going to find it? It is IL square or I square into RL. And you all know that the power dissipated in pure reactance is equal to 0. Either it is inductive reactance or pure inductance, or in pure capacitance, the power dissipation will be equal to 0. So that the power dissipation happens only in case of the resistance, and hence we use the expression I square into RL. So once you write this, you get the expression V Thevenin square divided by RL plus R Thevenin the whole square plus ZL plus Z Thevenin the whole square. So why exactly we are going to get it? This whole thing, if you square it, see, you are going to square the whole thing, then what is it we are going to get here? RL plus R Thevenin the whole square plus XL plus X Thevenin the whole square. RL plus R Thevenin the whole square plus XL plus X Thevenin the whole square is nothing but equal to, actually you know that the impedance Z is equal to square root of R square plus X square, or Z square is equal to R square plus X square. That's what is being done here. It is RL plus R Thevenin the whole square plus ZL plus Z Thevenin the whole square. The J term disappeared there. It won't be there. So you can verify it by using the expression for Z, which is equal to the square root of R square plus X square. Okay. So you have the expression for power delivered to the load circuit. Once you have this expression, differentiate this expression with respect to RL separately and XL separately, and then get the condition. So it is actually XL plus X Thevenin. It's not ZL plus Z Thevenin. It should be XL plus X Thevenin. So next, for maximum power transfer, the above equation, it must be differentiated with respect to XL and equated to 0. Then, so having done that, you can just do that procedure, dou PL by dou XL if you do it. So you get this particular expression, XL plus X Thevenin is equal to 0, or XL is equal to minus X Thevenin. So substitute XL equal to minus X Thevenin in the expression. So you get PL is equal to so and so. So for the exact understanding of this, let me just derive it for your analysis part. So it is PL, which is equal to V Thevenin square into RL divided by RL plus R Thevenin the whole square plus XL plus X Thevenin the whole square. This is the expression we are going to have it. So now we have to differentiate this with respect to XL. So since we have to differentiate it with respect to XL, then I'm going to get this as dou PL by dou XL should be equal to 0. So denominator square RL plus R Thevenin square plus XL plus X Thevenin square, this whole square in the denominator, and in the numerator you have V Thevenin square as it is. So first, keeping the denominator as it is, differentiate the numerator, since in the numerator whatever you are having is RL and not XL. that part is equal to 0. Then minus, keeping the numerator as it is, that is RL, you have to differentiate the denominator. So denominator, if you just find it, it is equal to 2 times XL plus X Thevenin. RL, actually this is RL into 2 XL plus X Thevenin. Since this part do not have XL term, we can, even if you try to differentiate it, this part is equal to 0. So that you have minus RL into 2 XL plus X Thevenin. That's what we are going to have it. And again, if you differentiate XL, it is equal to 1. So that is what is the thing we have. Then cross multiplying this part, if you cross multiply, this is being equal to 0. Then what is it I'm going to have? It is 0, which is equal to minus V Thevenin square into, or 2 times V Thevenin square into RL, that whole thing multiplied with XL plus X Thevenin. That's what we are going to have it. Again, this, if you divide it by this, finally I am going to get XL plus X Thevenin is equal to 0, or when the reactance XL is equal to minus X Thevenin. This is very important. And this is equal to minus X Thevenin. That is the thing, we have done it in our next case. You can just observe XL, you can just observe here, XL plus X Thevenin is equal to 0. The same thing we have done, or XL is equal to minus X Thevenin. So once you find this, substituting the value of XL in the expression, in the previous expression. So here, if you substitute XL is equal to minus X Thevenin, so then this part is going to become 0. That is, the term associated with J, or this particular part is going to become 0. So then we have only the expression PL is equal to V Thevenin square into RL by RL plus R Thevenin. So again, if you take the derivative of this with respect to RL, it is almost similar to the first derivation whatever we did. So it is RL plus R Thevenin is equal to 2RL. The same thing you are going to get it, and RL is equal to R Thevenin. So if you just observe the value of the impedance for, that is in case of an AC circuit, you say that XL should be equal to minus X Thevenin and RL should be equal to R Thevenin. So substituting that, you get this impedance ZL will be equal to R Thevenin minus JX Thevenin. The series impedance value is R Thevenin plus JX Thevenin, and the load impedance value will be equal to R Thevenin minus JX Thevenin, which by looking at it, you can come to a conclusion that it is the complex conjugate of the Thevenin's equivalent impedance, and hence the second statement says the maximum power will be transferred to the load circuit when it is an AC circuit. Both series impedance and the load impedances exist. In that case, the maximum power will be transferred to the load when the load impedance is equal to the complex conjugate of the source impedance, that is ZL is equal to Z Thevenin. This asterisk mark states that it is the conjugate. Then the maximum power, it will be either V Thevenin square by 4 R Thevenin, or you can also use RL. Both the expression remains the same. So that is regarding the second statement. Then before we start working on the problems by applying maximum power transfer theorem, the third condition should also be considered here. So for the third condition, wherein the circuit is consisting of only the resistance and no impedance is present, in that case I can write the circuit and the derivations similarly here. The circuit is AC circuit. It is, let me call it as V Thevenin itself, because after simplifying a complex network, let us assume that we have got the circuit which is the Thevenin's equivalent, here V Thevenin, and this is Z Thevenin, which is equal to R Thevenin plus J X Thevenin. I'm having, to this if I have only a resistance connected, this is, I call it as RL. So the load resistance, only the load resistance is connected. Then you have to find out the current I through the circuit. Current I through the circuit is nothing but equal to V Thevenin divided by, so total impedance in the circuit is nothing but equal to R Thevenin plus RL, R Thevenin plus RL plus J X Thevenin. So this is the expression for current I. So once you find the current I square is equal to V Thevenin square by R Thevenin plus RL the whole square plus X Thevenin the whole square plus X Thevenin square. Then the maximum power or the power delivered to the load PL is equal to I square RL, or that is equal to V Thevenin square by R Thevenin plus RL the whole square plus X Thevenin square into RL, that into RL. Now for maximum power transfer to the load, the partial differentiating this expression with respect to RL, because RL is the load resistance which is variable. So in this case RL is variable. So differentiating this equation with respect to RL, dou PL by dou RL is equal to, it should be equal to 0. So differentiate that, you get R Thevenin plus RL the whole square plus X Thevenin square, this whole thing square, and keeping the numerator denominator as it is, R Thevenin plus RL the whole square plus X Thevenin square, differentiate the numerator. So if you differentiate it, it is V Thevenin square into RL we have it, so it is V Thevenin square, and keeping the numerator as it is, so it is V Thevenin square into RL, this numerator as it is, differentiating the denominator, the second part I am not going to have it, only this I can write here, 2, it is 2 multiplied with RL plus R Thevenin. So if I write it properly, taking V Thevenin square as a common factor, I can write the numerator part as R Thevenin plus RL the whole square plus X Thevenin square minus V Thevenin square, I have already taken it out, 2 into RL multiplied with RL plus R Thevenin, that must be equal to 0, because this if you cross multiply, that part is going to become 0. So you are going to have only this part. Again V Thevenin square part will also be cancelled over there, because you are dividing this by 0 by V Thevenin square, again that's going to become 0. So you are going to have 2 RL square if I multiply that plus 2 RL R Thevenin is equal to, that is, this I have taken it to the left hand side, this as it is I am maintaining. So it is RL square plus R Thevenin square plus 2 RL R Thevenin. So expanding this plus X Thevenin square. Now you can observe 2 RL R Thevenin on left hand side gets cancelled with 2 RL R Thevenin on the right hand side. so that gets cancelled. So then I'm going to have RL square on one side and R Thevenin and X Thevenin square on the other side. So here I'm having 2 RL square and the right hand side I'm having RL square. So 2 RL square minus RL square gives me the value equal to RL square, which is equal to R Thevenin square plus X Thevenin square. R Thevenin square plus X Thevenin square. RL is equal to square root of R Thevenin square plus X Thevenin square. So the meaning of this, square root of R Thevenin square plus X Thevenin square is equal to RL. So meaning it is absolute magnitude of the source impedance. So when the load resistance is equal to the absolute magnitude of the source impedance, the maximum power will be transferred to the load circuit when you have the load as a resistance itself. So this is the third case. After this, let us try solving the problems by applying maximum power transfer theorem. The first problem, the maximum power transfer theorem. The first problem for the maximum power transfer theorem, I'm having, let us first go for the statement of the problem. Determine the value of RL for maximum power transfer and also find the maximum power transferred. It's a DC circuit. So let me write the circuit here again. It's a DC circuit. The value of the voltage is 50 volts. The circuit is somewhat similar to this. (10 ohms, 5 ohms, 2 ohms, 3 ohms). Then the load is connected between the terminals A and B, and this is a variable resistance. This is the circuit. Now, how to solve the problem here? In order to solve the problem, the first important step is to replace RL from the circuit, because I have to find out the value of RL itself. To find out the value of RL, this entire circuit here, whatever I am having, should be replaced by a single voltage source in series with a single resistance. In order to replace the entire circuit by single voltage source in series with a single resistance, it is Thevenin's equivalent circuit. So for that purpose, let us first remove RL from the circuit. Removing RL from the circuit, an open circuit is created between these 2 points. So since an open circuit is created between those 2 points, so find out the current through 3 ohms resistor. The current through 3 ohms resistor multiplied with 3 ohms gives you the open circuit voltage. That is your single voltage source. Then find out Thevenin's equivalent resistance later on. So now first step is you find 3 and 2. They are in series. Together they are in parallel with 5 ohms resistor. So that this circuit I can further reduce as a 50 volt source in series with 10 ohms resistance. This is 5 in parallel with 5 gives me the value as 2.5 ohms. So after finding this, find the current I. This is the total current I at this point. Okay. So the current I is equal to 50 divided by 10 plus 2.5, which is equal to 12.5. 50 divided by 12.5 gives me the value equal to 4 amperes. So this 4 amperes enters at this point, that gets divided between these two. Since both of them are having the equal resistance value, the current through both the branches, it divides equally. So that current through 3 ohm resistor must be equal to that current of 4 amperes multiplied with the resistance of the opposite branch, that is 5. Sum of the resistances, once again it is equal to 10. So this must be equal to 2 amperes. So the current of 2 amperes flows through 3 ohms resistor. So after finding the current, find out Thevenin's equivalent voltage V Thevenin, which is equal to 3 multiplied with 2 amperes, which is 6 volts. So we have got the Thevenin's equivalent voltage, which is equal to 6 volts. The next step is to find out the Thevenin's equivalent impedance. So in order to find out the Thevenin's equivalent resistance over here, short that 50 volt source and looking into the circuit from the terminals here. That is, by sending a current at this point, I find these two, that is 2 ohms and 3 ohms, they are in parallel. Again, the same current that which is flowing through 2 ohms flows through this. So I find that 10 and 5 in parallel. So R Thevenin in this case is 10 into 5 divided by 15. Okay. So that parallel combination will be in series with 2 ohms resistance. Okay. So after that, again that is in parallel with 3 ohm resistance. So if you just try to find out the value of this value will be equal to 1.92 ohms. That is Thevenin's equivalent. I repeat, when you send a current at this point, you can find that at this junction it divides between 2 ohms and 3 ohms resistance. The current which is flowing through 2 ohms again at this junction divides between 10 and 5 ohms. So that 10 ohms is in parallel with 5 ohms resistor. After reducing that will be in series with 2 ohms. Again that combination will be in parallel with 3 ohms. So when you calculate everything, you find the value equal to 1.92 ohms. So the value of RL is equal to 1.92. So once you find the value of RL, replace this entire circuit by V Thevenin and R Thevenin with RL. So R Thevenin is 1.92 and RL is also equal to 1.92 ohms, and the value here, the voltage value here is equal to 6 volts. So then the next step is to find out the maximum power which is being transferred. We have already derived the expression for the maximum power that's going to be transferred, which is nothing but equal to V Thevenin square by 4 RL. That is the maximum power transferred to the load resistance. So PL is equal to 6 square divided by 4 into 1.92. So after calculating that, the value will become equal to 4.67 watts. So that is the power which is being transferred to the load circuit. So this is the way we can solve for DC circuit. So next, moving on to the next problem, we'll try solving an AC circuit here. For AC circuit, how exactly we have to do it? That is the second condition. In case of AC circuit, which is the second condition, we have the circuit with 50 at an angle 0 volts. 50 at an angle 0 volts. Then I have 5 ohm resistor in series with J5 ohms reactance, and ZL is connected between these 2 points. Then I have 3 minus J4 minus J4 ohms. Then to this I have one more source of 25 at 90 degrees. at 90 degrees. So in this case, you can just find there are 2 voltage sources. One is 50 at an angle 0, the other one is 25 at an angle 90 degrees, and you have ZL connected in between the two impedances and the two sources over there. So 5 ohms in series with J5, 3 in series with minus J4. So now the first step is to get Thevenin's equivalent circuit. After finding Thevenin's equivalent circuit, the next step is to find out the Thevenin's equivalent impedance, and hence after that find out the total power which is being transferred. So for that, first you have to find out the Thevenin's equivalent voltage. So remove ZL from the circuit, creating an open circuit. So in that case, you are going to find a single series circuit. Only one loop is existing there, only single voltage. When single loop is there, you can find out the current I in the first case, which is equal to 50. There are two sources, both of them, I have not marked the polarity, both of them are having the positive polarity in the upward position. So that 50 at an angle 0 minus 25 at an angle 90 is the voltage, total voltage applied to the circuit. That whole thing divided by 5 plus 3, the real parts I am adding it, so it is 8, and subtracting. Here actually you have to add the imaginary part separately. So one is positive, the other one is negative, so that I am going to get 8 plus J1. So this is the amount of the current flowing through the circuit. So once you find the amount of the current flowing through the circuit, the next step is to find out the drop between these 2 points. I call it as A and B, the voltage between these 2 points. This can be either this voltage source minus the drop across this, or this voltage source plus or minus the drop across this. Depending upon the direction of the current, it will be either plus or minus. So for this case, actually the current is flowing from left to right, and hence I can say this is minus to plus, so plus, again this is plus. So 25 at an angle 90 plus the drop across this, or 50 at an angle 0 minus the drop across this. So my V Thevenin in this case will be equal to 50, that is 50 volts, 50 at an angle 0 minus I, whatever the value we have just now calculated, that into 5 plus J5, 5 plus J5, or this is also equal to 25 at an angle 90 plus I into 3 minus J4. Both the ways you should get the same voltage. So next you have to find out the Thevenin's equivalent impedance. So in order to find out the Thevenin's equivalent impedance, short both the voltage sources. Okay, now send the current through the output terminal. So you find that the impedance 5 plus J5 is in parallel with 3 minus J4. So your Z Thevenin is equal to 5 plus J5 in parallel with 3 minus J4. 3 minus J4. So after solving it, you are going to find ZL as 4.23 plus J 1.15 ohms. That's a value you are going to find out. The next thing is replacing the circuit by Thevenin's equivalent and connecting this impedance over there and finding out the power which is being transferred to the circuit, and the value that you are going to find out there in this particular case is equal to 5.68 watts. So summarizing, I have reviewed the Thevenin's theorem statement, Norton's theorem, and how exactly what is the purpose of using Thevenin's theorem and Norton's theorem there. Then the statement of maximum power transfer theorem we have done. We also have proved the maximum power transfer theorem for all the 3 cases, then solved 2 problems, one DC circuit and the other one is AC circuit. So in our next session, we solve some more problems on maximum power transfer theorem and then move on to the next theorem, which is superposition theorem. So with that, thank you so much.